Hello, let's make Frogger.
Frogger is a game where you have to guide a small amphibian to safety by making him cross a main road. You then also have to get him to cross a river, and the river clearly has quite strange currents by jumping on the logs. And the difference here, of course, is when the frog jumps on the log carries him along. And, oops, fell into the river though, have to try again. And the point of the game was to get the frog to safety at the other side of the river. And as you can probably tell, I'm not very good at it. It's quite challenging. Let's try these logs again. Here we go. And to get him to safety, you just have to park him somewhere in one of the safe zones. Now, unusually for this channel, this game is a lot more graphical. And you won't need any third-party libraries. Everything here is done in the command prompt. In fact, it's all just very subtly disguised ASCII art.
In this video we're going to look at the separation between graphics and game logic. First we'll implement the rules that make Frogger the game, and then based on the output of these rules we'll add the graphics. And what we'll see is that adding graphics to anything can double the size of your code base. Let's get started.
As you must know by now, we're going to include the OLC console game engine. And if you don't know what that is, please check the little box above. But in a nutshell, it just allows me to wrap up the console in such a way that I can output text to it very quickly and get keyboard input. I've created a base class called oneLoneCoder_Frogger, which inherits from the OLC console game engine, and this class has two methods, onUserCreate and onUserUpdate. And onUserUpdate is called once per frame. And I'm going to construct a console which is 128 characters wide by 80 characters high, and each character is going to be 12 by 12 pixels, not the usual 8 by 8. Now there are probably several ways to implement Frogger, and the first way you might think of doing such a game is to have lots of objects, such as cars and lorries, and the frog, and you'd look for collisions between them. So for example, we could have a car object here, and another car object here. And up here we could have a bus object, and up here eventually we have logs. And up here finally walls. And for each object we would store some properties, so we might store the position, x and y, and we might store a velocity. We'll call that vx and vy, and our frog will also be an object. And as the frog jumps around the screen, we basically just check for overlapping collisions between rectangles. And each frame we update the object's positions according to their velocity.
This is quite a modern approach, and it's completely valid, but there's some problems.
In particular, the problems start when the objects go on and off the screen. For example, once this bus object has travelled off the screen, we have to detect the fact that it has travelled off the screen, and then relocate it somewhere over here. And there are multiple objects that do this, and so we would have to devise some sort of object manager. A second problem is that the sequences we see on screen will become very repetitive, and therefore very predictable. So if every time this bus object goes off the screen, we place it in the same location over here, we're just going to see the same buses going past with the same pattern. This could be very predictable and quite boring. Using this object management approach, we could of course choose a random position to place this somewhere else down here. But if it's too far, then there might be quite large gaps between the objects. And as soon as we start introducing randomness into the game, we then have to make sure that we're not randomly placing a bus that's overlapping a bus that's already off the screen. And as you can see, the thing gets quite messy. And finally, we would need to find some way of parameterizing all of these properties to give us different difficulties as we progress through the game. So we'd need the density or probability of buses that appear, the probability of cars that appear, how far back do they get reset.
Whereas there is nothing wrong with this approach, I think it seems quite cumbersome, and I think I'm going to try it a different way.
My approach requires that we break up the playing field into lanes. And each lane is associated with a velocity, which if it's positive means the lane moves in this direction, and if it's negative, the lane moves in this direction. Each lane is only capable of showing one type of obstacle, so in this lane I'm going to have cars, And in this lane I'm going to have cars, and this one might be a bus, and this one might be logs, etc, etc. And instead of storing the individual objects, each lane is going to be a sequence of safe or not safe cells. So let's, for example, say these two cells are not safe, however this next one is. And this one, these two again, not safe. We'll have a bit of a gap. Not safe, not safe. And all of these cells are equally spaced apart. I'll just mark the safe ones with a tick. And we keep doing this even beyond the screen, so we have lanes that are quite long, but we're only going to show a selected portion of them to the player. When our frog makes a movement, it will check, is it moving into a location that is safe or not? If it is, we can move the frog. If it's not, we kill the frog. Oh dear. If we take this yellow dashed area to represent the viewing field, we can see that the lane is typically much larger. And as we scroll the lane along according to its velocity value, we can simply take the last element and replace it, like a circular queue. This will mean that a single lane will have a repeating cyclic pattern.
Now you might think that this approach would look very repetitive, and indeed it will for a single lane, so the player can become familiar with the traffic pattern for that lane. However, each lane operates at its own velocity, and the combination of lanes and velocities give rise to a very random looking playing field. So it's got some local familiarity, but some global randomness.
Let's start by developing a way to store the level data. And I'm going to do this by storing a vector of pairs. And each pair is split into a float that represents the velocity for that lane and a W string. And we'll call this vector vec_lanes. And it's nice to do it this way because we can initialize it. And by being very visual about the initialization, we can make sure that the level looks about right. So if we're initializing this vector statically, we have to have internal braces like this to represent the pair. Now I've chosen for my version of Frogger that we're going to have 10 lanes visible on the screen. So I'll just prepare these to start. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And just because I'm fussy, I'll space that one back out. So what's the string for? Well, I'm going to use the string to store my lane information as being safe or not safe. So is it safe for the frog to step into, or is there an obstacle there? And if it's safe, I'm going to use a space, and if there's an obstacle, I'm going to use an X. So at the moment, we'll assume that there's obstacles which are 2 cells wide, and we'll have a bunch of them. In fact, for each lane, I'm going to store 64 elements. Let's throw in some comments so we can remember what these are. So these are cars. So we've dealt with the road, now we'll deal with the river, and it's exactly the same principle, except this time the X's will represent logs. Now you'll notice I've missed a few out. So the bottom and middle lanes, these are just going to be pavement. There's never any obstacles. These are sort of an area of respite the player can use. So these just get filled in with no obstacles, i.e. just dots. And this top one needs to be filled in with the safe areas. So mostly it is wall, and of course they're not safe. So we classify wall as an X, and we're going to leave 2 gaps for a safe cell, and we'll fill in the rest as obstacle. So if we look at this data map, what we can see is really the player screen is only going to be represented by this much space that I've highlighted in blue. And all of these lanes are going to be scrolling around, so the end of them will be going back to the start at different velocities, which will give us an interesting looking grating appearance to the level. So we need to decide what the velocities are. Well, we'll start at the beginning here, which is a pavement. Of course, that doesn't move, it has no velocity. For the first row of cars, we'll move those at 2, so they should move in this direction. The next row of cars we'll have at -4. And I will just delete that so we can keep the level data all justified. We'll set this velocity to 3, -3. Again, here we've got a pavement, so there is no velocity, nothing needs to move. 2, 3, and -3. And of course the walls don't move either.
Let's now have a think about how we can draw this lane information to the screen. Even though we're pretending it's a circular queue of sorts, that would actually be quite inconvenient to detect when a cell is no longer visible and then pop it off one side of the queue and push it to the other side. So instead I'm going to use some clever indexing based on the elapsed time of the game so far.
To draw the lanes, I'm just going to iterate through them. So I'm going to use little auto here, lane, from my vector of lanes. I'm also going to require a variable that has stored the total elapsed time since the start of the game. I'll initialize it to 0, but this is simple enough to maintain because all we need to do is accumulate it in the onUserUpdate function. Times its start plus equals f elapsed time. Now currently our cells are represented by a 1 unit in game space. That doesn't necessarily scale up to screen space, so we need to decide how big one game unit is. And I'm going to do this simply by storing a variable called cell size. And we'll say that one game unit is 8 characters across on our screen. And conveniently, we've chosen screen dimensions, which are multiples of 8. So how do we know where to start? We need to find the offset for the lane. I'll create a variable called endStartPos. And simply put, this is going to be the integer version of the time since start multiplied by the velocity for that lane, which was the first component of the pair. And this is a simple integration of the velocity, because we have seconds times units per second. All we're left with is the units. That gives us a physical offset. But of course our lanes have a maximum size, so we'll make sure it wraps around, and we know that the maximum size is 64. Easily achieved with the modulus operator. Now that I know my starting point, I can draw the cells to the screen. So I'm taking the width of the screen and breaking it up into the number of cells across. And I'm going to iterate through them. I'm going to represent the cells as being either X's or full stops again. But I need to work out which is which. So to do this, I'm taking the current lane I'm working with and taking the second element, which, if you remember, is the W string. And I can treat this as an array. And now I've calculated my start pos, and I know my offset into the number of cells going across the screen, which is I know where to start in the string. But I have to be careful here. I also need to use the modulus operator again to make sure I don't go beyond the length of the string. So I know in the left-hand side of the screen is always going to be a smaller index than the right-hand side of the screen. I'm going to add an X and a Y variable so we can keep track of which cell that we're drawing. I feel this might be useful later on, and don't forget I can see into the future, of course. And to draw the actual tile, I'm going to use the fill function, where the first two arguments are the coordinates of the top left of the cell, and the second two are the bottom right. And I'm just going to draw the character either full stop or an X, determined on the position of the string. Now, it's a good job I had these coordinates, because I'm going to need to increment my Y for each lane. Let's take a look and see what happens. Oh dear. Well, I can see before it crashed that rather pleasingly we have got cells of X's and full stops, and these will be somewhat based on the patterns that we saw earlier. However, string subscript out of range. Why is this? Well, if I enter the debugger, I can see that my end start position is -1. And in C++, -1 mod something doesn't quite give you the answer you expect. In this case, I'd like it to give me 63, because -1 would represent the other end of the string. And why is it -1 in the first place? Well, that's because for this lane, the velocity is negative. To compensate for the incorrect answer when doing a modulus with a negative number, we'll have to do it manually. And so if the start position is negative, i.e. the velocity was negative, we take the absolute position of it. So in this case, if it was -2, for example, we take it as a +2, and we double check the modulus again. And we subtract that +2 from the width of the string, which in this case would give us the answer that we want, which would be 62. Let's take a look again. So now you can see the game is operating without crashing, and we can see blocks moving across the screen. I'm sure the YouTube compression algorithm is loving this. If we start at the bottom row, here we see we've got the pavement. We don't see anything happening. We've got a row of cars represented by blocks of 2, then another row of cars moving in the opposite direction. Then we've got a row of buses. These are represented by 4 blocks. Then some cars, then the pavement again, then 3 rows of logs, and finally some safe spaces and walls at the top, but no graphics yet.
There's also something else not quite right here. It's not very smooth. All we've done is scale up everything by a factor of 8 using that end cell size variable, which results in everything moving by blocks of 8. Given that our cells are actually 8 characters wide, why can't we move them 1 character at a time? Well, of course we can.
Now the line responsible for this blocky behaviour is here, where we're taking our nice continuous floating point f times start, and we're casting it to an integer. This calculation will of course have a result that contains values beyond the decimal point, and we can use these fractional values as our offset into our integer space. So I'm going to create a variable called nCellOffset, and it's an integer, and to calculate the offset I'm going to bodge in a little bit of fixed point mathematics. I'm going to scale up our start pos equation by a factor of 8. Times in start times lane.first. Exactly the same as above. But now I've scaled it up, I'm also then going to do the modulus by 8. But where do these 8s come from? Well, in fact, they are n cell size. Now I appreciate that this line of code may be a little tricky to interpret, but what it does is scale the remainder of this calculation by the n cell size and modulates it by the n cell size, so we know that our remainder will be an integer value within the range of cell size. So 0.5 becomes 4 in this case because it's half a cell size. 0.25 therefore becomes 2. Since we now have a cell offset, we need to apply that to our drawing calculation, and we'll only need to apply that in the x-axis, because nothing moves up and down, other than the frog, and we'll come to that later. So we'll subtract from that x-coordinate, and we'll subtract from this x-coordinate. Let's take a look. Well, that's very nice. We can now see much smoother movement. But there's some odd behaviour, particularly at the boundaries of the screen. We can see items literally bursting into existence and disappearing prematurely. So let's try and examine why this is. I think we're being confused because we're seeing the merging of 2 frames. Just to separate this out, I'm going to clear the screen before each draw. And to do that, I just use the fill function, and I'm going to draw a space everywhere. And this is quite nice now because it shows us the cell offset working. Objects leaving the screen do so smoothly, because as it's drawing the cell at the edge of the screen, it's being pushed along by the offset that we've calculated. On the other hand, objects which are appearing on the screen start to appear already within the screen. They don't smoothly transition in, because this boundary here, for example, is already offset by the cell offset, so the next cell immediately changes from periods to an X.
To overcome this, we're going to use a good old-fashioned hack. I could try and create some clipping routines to be as efficient as possible, but instead what I'm going to do is just start drawing one cell earlier off the screen.
And if we look at this fill routine, which is drawing the individual tiles, we can see we've got an X variable here that we don't do anything with. I'm going to create a fixed offset here by initializing our X to -1. Well, we can see we now get smooth transitions on the left-hand side of the screen, but we're simply not drawing enough cells over. We've shifted the whole screen to the left by -1. The gaps on the right-hand side of the screen are caused because we're simply not drawing enough tiles. We've already offset everything by -1, and we know that we need an additional tile to cover up the boundaries caused by end cell offset, so we want to draw an extra 2 tiles on the right-hand side. Let's take a look. Perfect, we've now got smooth transitions across the whole screen.
Full stops and X's are great at showing us that the game is kind of working, but it's not very pretty on the eye. So let's start adding some graphics, and to do this I'm going to introduce a little tool that I've built, my one-line coder sprite editor, which of course is based at the command prompt and it does everything using ASCII art, but it's a little bit more visual, it's easier to create some sprites.
I'll probably do a video about the sprite editor in its own right at some point later on, but suffice to say, it's a very simple program. It allows you to move a cursor around on the screen and place different coloured blocks, and it'll also save and load sprite files to disk. And this is what the sprite editor looks like. It's got some dots and a cursor I can move around with the arrow keys, and I press the spacebar to place a pixel. In fact, I can use page up and page down. I can zoom in too. If I press the F9 key, I'm loading up a sprite that I've already created, and it is the car. And this car is 16 pixels wide by 8 pixels high. Conveniently, 2 of our game cells. Sprites created by the sprite editor are stored in a class called OLC Sprite, and this has been a modification to the OLC console game engine. So if you've already got the source code for this from the GitHub, go and get it again. And I'm going to create an object of OLC Sprite called SpriteCar2, which is my pink car. I only want to load sprites once, so we'll use the onUserCreate function to do this. And it's simply a case of passing the file path to the constructor of OLC Sprite.
Now we're introducing graphics, we've reached a limitation of our game engine. Our lane data only contains full stops and X's for safe or not safe. But conveniently, these are already arranged in a tile-like fashion. So I'm suggesting that we change the X's to represent different sprites.
Let's nominate this lane as being our fast car, the pink car. We can see already that we've got blocks in groups of 2 that represent the fast car object. But we need to tell it that there's a different sprite. Now each cell is only 8 by 8 characters, and our car is 16 by 8, so we need to specify 2 halves of the car. I've used the Z character to specify one half and X to specify the other. Instead of just filling the cell with the character from the correct point in the string, I'm going to use the character in a switch statement. So we know that for the case of the character being Z, we want to draw the sprite of the front of the car. And to do this, we're going to use a function in the one-line coder game engine called drawPartialSprite. And the drawPartialSprite will take the same X and Y coordinates that we've already calculated before, so I'm just going to cut and paste those in. But it takes a few more arguments, so the first one is the actual sprite object itself. Sprite car2 in this instance. And the reason it's draw partial sprite is we can choose which area of the sprite we want to draw. So we only want to draw the first half of it for this. So we're specifying the top left coordinate of being 0, 0, and the bottom right coordinate of being 8 by 8. And that's all we need to do to draw one half of the car. So we can break. To draw the other half of the car, we can cut and paste this line. It's exactly the same code, except in this time we're looking for the X. And we want to specify the second half of the sprite. Let's take a look. Well, lots of pink things going on. So we can see that we get half the cars for most of the places, and that's because we've got X's representing other things at the moment. But for one lane, the one lane where we've added the Z's, we can see we've got a complete car. But it's going backwards, of course it is. Rather than changing the graphic for the car, I'm just going to change the velocity of the lane from a minus to a plus. Let's try again. And now we can see the car moving smoothly in the correct direction.
I'm going to add in the other sprites now, and I'll fast forward through this bit because it's very repetitive. And this is my problem with graphics, is most of the code now will become about the graphics and less about the game engine. Phew, right, let's take a look.
Well, it's certainly a lot more visual. We can see we've got traffic and we've got different types of cars and buses. And we haven't got any water yet, so I'll have to look at why that is. And we've got the brick walls and the home spaces at the end, starting to look a bit like a game. You'll notice that in the logs I've used the same sprite for the central parts of the logs, but I've used different ones for the ends. This was reflected in the code. For example here, I've got JLLLK. So I can have the logs as long as I would like. But we were missing our water, and that's because I'm using the full stop character, which is also road. So I'll just change those over from full stops to, I'll use commas, why not? I've got nothing else, comma. Let's try that again then. Much better, we've got water. I'd like to also mention before I forget that one of the reasons I've chosen a lower resolution on this example is I get these artificial scan lines which make it look particularly retro.
I like that.
Whilst the program is currently a visually pleasing demonstration in the console, it's lacking its main protagonist, the frog, so let's add him in. I'm going to create two variables, fFrogX and fFrogY. And I'll initialize these to 8 and 9, which is at the bottom of the screen on the pavement.
The frog is only going to be one game unit, i.e. one tile, in both his width and his height, and we can use this to our advantage.
The frog is not subject to any of the offset problems that we had with the tiles. In fact, the frog moves one tile at a time. And it's this that gives the game its bit of challenge, as the player has to estimate, is there enough space to fit the frog. To draw the frog, I'm going to very simply call the draw sprite routine. This is built into the console game engine, and it just takes an X and Y coordinate and the sprite. Let's say hello to the frog. There he is at the bottom. Hello. We can replace this screen clear now with code to handle the frog's movement. And this is very simple. We look for a released event on the up, down, left and right key. And we simply alter the frog's variable accordingly. So up and down moves him vertically up and down the screen, we change our y coordinate, and similar for x. Let's have a look. So there's our frog, and he moves one cell at a time. There's no collision detection at the moment, so our frog can't be killed. But before we add in collision detection, we've got one dynamic to add to the frog's behaviour, and that is how do we get the frog to ride on the logs? We know that each lane comes with a velocity, and if the frog happens to be in these top 3 lanes here where the logs are, we want to move him by the same velocity. We don't need to do this for the roads, because the roads don't move. So after we've accepted the user input, we're going to move the frog if any of the lanes that he's on currently affect his x position. And so I take the velocity for the lane, which was the first element of the pair. I know which lane it is because the frog's y coordinate can be casted to an integer, and I simply offset the frog by that amount, modulated by f elapsed time. Let's just try that out. So as I move the frog, we see on the roads he does nothing, but if I move him onto the water, he moves at the same speed as the water, and in the right direction.
Now we need to kill the frog.
Our frog is going to die if he touches anything that's not considered safe. So I'm going to create a second buffer, which is the same size as the screen buffer, called buffer danger.
And this will be similar to the buffer we had right at the start, which was just full stops and X's. And we'll need to construct it for each frame, because all of the things will move around. We create a static buffer full of safe or not safe, and we check whether the frog is safe or not safe.
The danger buffer will be created on the onUserCreate function, and I'm simply just creating an array of booleans, which is the same dimension of the screen, and I'm setting them all initially to false. Now, in a very similar way to the fill function we used earlier to draw the character representation of the cell, instead of drawing to the screen, I'm going to draw to the danger buffer. And so this first bit of code iterates through each element of the cell, so effectively it's an 8x8 matrix, which is offset depending on the screen position and the individual tile offsets. This line of code is effectively clipping our coordinates j and k against the screen buffer, but it's targeted at our danger buffer. The fill routine as part of the console game engine clips behind the scenes, so that's why we could get away with drawing things off the screen. They simply just were evaporated away. We need to do that manually here, so I'm just checking that the j and k coordinates are within the boundaries of our danger buffer. And if they are, then we need to decide, is the current cell actually dangerous or not? So using my screen space coordinates j and k, I can calculate where in my danger buffer I am. And so I just need to decide if there's actually danger there. And we have the graphic variable that we used earlier to decide which sprite to draw. And simply put, some sprites are safe and some are not. Let's format these to make them a little bit more readable. We know that if the graphic, for example, was equal to a full stop, that represents road, so that's safe. What else have we got that's safe? Well, we also know that the log was safe. But the logs consist of 3 different components. We know that we've got j, k, and L. Of course, the pavements are safe, and it goes without saying that the frog will always be safe at home. So all of those are safe locations, so they're not danger. We can invert the whole lot.
The best time to check if the frog is in danger is after we've moved it.
And because of the simple dynamics of the frog, we can do this with just simply checking the 4 corners. To keep the code readable, I'm going to separate these out. So I'm going to extract the top left corner of the frog. And to do this, we take the frog's y coordinate and times it by the screen width and plus the frog's x coordinate. Of course, everything is expanded by cell size, and we use this as an index into our danger buffer. And I can use similar code for all 4 corners. Top left, top right, bottom left, and bottom right. We can see that the top ones in the y don't have any augmentation to the frog, but the bottom ones, it's the frog plus 1, effectively becoming the cell below. I've decided to give the player just a bit of a chance, so I'm not checking against the extreme four corners, I'm checking against the four corners 1 pixel in from the edge of the frog. So I do that on both the X and the Y. And very simply, if the frog gets squished or drowns or anything else, we reset to the start position.
In my version of Frogger, all you have to do is get the frog from the bottom of the screen to the top of the screen. You've got an infinite number of lives to do it. In the real version of Frogger, you had a fixed number of frogs to get across from the bottom to the top. And as you safely got a frog home, that safe zone became unavailable to place any more frogs. I'm not going to show how to do that in this video, and I'll leave it to you guys to figure out.
Let's check that our collision detection is working. So there's the frog. I'm going to get him hit, and he resets back to the start. So it looks good. Let's just double check that. Oh, now it's difficult to test your own games when the game itself is quite challenging. Let's get the frog over to the other side, and he can rest on a log, but if he jumps in the water, he's dead.
And so there you have it. A fairly graphical version of Frogger in the command line in about 150 lines of code. By carefully planning how we were going to represent the levels, we managed to get away from needing a complex object manager, and we also stayed away from the need to implement a partial physics engine. The way that we store the level is amenable to having different levels with different types of obstacles and different levels of difficulty in the future. And by exploiting a parity between unit space and screen space, we can control the frog very simply. As always, all the code is available on GitHub from the links below. If you've enjoyed this video, please give me a thumbs up and have a think about subscribing, and I'll see you next time.